Hi guys, today we are going to talk about kinetic energy. So kinetic energy, if you look at the back of this board, you can see the equation. If you Google it, you can see that our equation for kinetic energy is going to be 1/2 mv squared. Today I want to dive into why is that our equation and how can we use it, and then combine it with some of the other equations we've already learned. So wrapping up our work versus velocity lab. We did a lab where you looked at, you had your track. Oops, if I could draw. Ooh, yikes. Clear that real quick. We looked at our lab where you guys had your track and you applied a force to the car and you looked at the force in the distance and then you released it and we were looking at the velocity. So if I look at that, you should have put work on one axis and velocity on another axis. Ideally, you got a nice quadratic curve when you did this. So to linearize this, we would need to square our velocity, which would give us a linear graph. Now, we know that this linear graph, it's going to have some sort of relationship of a slope. A slope's going to equal to m of some sort. Now, I'm going to take this idea of work, and that's on my y-axis, because if we line it up with our y equals mx plus b, work equals slope we don't know, our x-axis is v squared. Now, if I know that the work applied, it's actually that change in energy is going to be a kinetic energy. I'm going to change this to Ke, and I'm going to line this up with my kinetic energy equation, mv squared. So if we have a slope here, the energy that came out of the work being applied was kinetic energy. We have a v squared. So in your lab, your slope should have been equal to 1/2 the mass of your car, ideally. Now, it's not a perfect lab. We definitely had some error. But I would really encourage you to take a look at that to see, was your slope that you got for your lab 1/2 of your mass? This is really where that kinetic energy equation comes from. It's coming from the idea that a force and a distance, all of it changing into a kinetic energy, we can actually line that up to see that velocity is squared. So let's look at this another way. If your hand, and it's applying a positive work to a car, your hand is causing the car to increase. So we can do work from the hand on the car. That's what this is. Work from the hand on the car is going to be equal to the kinetic energy final minus my kinetic energy initial. If we look at a bar chart, we could look at it this way. This and the one we usually look at would be like the circle, and we'd see like these arrows going in. There's different ways to look at it. That's totally fine. But we can see that the kinetic energy initial plus this is equal to my kinetic energy final. We can rearrange that to see force times distance is equal to kf minus ki. The same idea that we started with, force distance is equal to our change in energy. We're just really defining what that specific type of energy is now, and we know that it's a kinetic energy. So we can say that force times distance is equal to the final minus initial. That's just what that change in energy looks like. So there's two different ways we can look at this. We could look at a constant applied force or that instant change like we saw in our lab. Both are totally fine. And we're going to look at how can we take all of these ideas and put them together. So what is kinetic energy? Kinetic energy is the of an object is K equals 1/2 mv squared. M is mass in kilograms, V is speed and velocity. Now I want to point out that kinetic energy is always, always, always positive, because when we square this velocity right here, even if it were moving in the negative direction, if you multiply a negative number by a negative number, you get a positive number. So our kinetic energy is always, always, always positive. Now we'll have gravitational energy that's not always positive, but kinetic energy is. Now to check our units, we know M is kilograms. Velocity is meters per second, but when we square that, we get meters squared over seconds squared. If we pull that meter out, like I did here, if we pull a meter out, we get a kilogram meter per second squared, which is the same thing as a Newton, because that's M and A. This one's A right here. That's where we can get a Newton meter. And then we know that a Newton meter is the same thing as a joule. So we can just check our units to make sure everything works out and that it agrees with what we already know about physics. So let's do a couple example problems. Example number 1, we've got a 4,000 kilogram elephant. It's riding a bicycle with a speed of 4 meters per second. Super realistic. Out of nowhere, a zebra runs in the elephant's path and he must slam on his brakes. If the bike brakes exert a force of 1.4 kilonewtons, how far is it going to take the elephant to stop its bike? So looking at this, I'm just thinking about my situation. I've got my elephant. Here's the trunk. Here's his ears. Riding a bicycle. I'm just going to make an elephant bike. There we go. We got our elephant riding a bicycle. And then he's going to stop. So he's moving. And then his velocity is 0. Thinking about an LOL chart here, I would have 4 boxes of kinetic energy, or however many you're choosing. And then I'd have none at the end because all of them would have left through work. So if I were to come up with an equation about this, I'd say kinetic energy is equal, or kinetic energy minus my work is going to be equal to 0. Sorry about that. So putting this into equations, I know that 1/2 mv squared, which is my kinetic energy equation, minus my work equation, force times distance, is going to be equal to 0. Now I have a force, I have a velocity, and I have a mass, and I need a distance. So I have all those things. I'm going to rearrange this. 1/2 mv squared is equal to F times d. So let's plug in what we know. 1/2 mass is 4,000. My velocity is 4 equals, and then 1.4 kilonewton is 1,400 newtons times distance. So let's plug that into our calculator. That's going to be a big number. So 4,000 times 1/2, that would be 2,000. And then 4 squared, 16. So 2,000 times 16. This gives me 32,000 equals 1,400 D. So I'm going to divide that by 1,400, which gives me a distance of 22.9 meters. So that's how long it would, how far my guy would go. So technically, we could have done this previously. We could have used kinematics and forces in conjunction with each other to do this. We could have used kinematics to solve for the acceleration, and then the acceleration to solve for, to figure out how far it went. Or we could just do energy. Energy is kind of like an in-between to where if we don't want to do multiple steps, we can just do it all in one. All right, let's keep going. My example 2 is you load an arrow of mass 0.09 kilograms into a bow and pull the bowstring back 0.4 meters. The bow has a spring constant of 900 newtons per meter. Determine how the arrow's speed as it leaves. So we're going to actually do some elastic with this. So at the beginning, if I'm thinking about an LOL chart, I've got some elastic energy. I'm just going to do 3 boxes because I'm running out of space. So I've got elastic energy, or you could say US, whatever, EE, US, whatever your flavor is. There's no energy if I'm going to choose the bow and everything as my system. Then afterwards, we have 3 boxes of kinetic energy. So this tells me, I'm going to switch to spring energy here. The spring energy is going to be equal to my kinetic energy. And we know from our previous lesson that spring energy is 1/2 kx squared equals our kinetic energy 1/2 mv squared. So we can do a little bit of fancy footwork. The 1/2s cancel because they're on both sides. My kinetic energy was, my spring constant was 900 times the 0.4 squared. We know the mass of my arrow is 0.09, and then we just have to solve for the velocity. So let's do that. 900 times 0.4 squared gives me 144. Now, technically that's not the energy because I got rid of the 1/2s on each side. So if they were to ask me, like, what's the spring energy, that's not 144. I'm just solving for my velocity here. And then we've got 0.09 v squared. So I'm going to divide that 0.09 to the other side, which gives me 1,600 equals v squared. And then I just need to square root that, 1,600, which gives me a velocity of 40 meters per second. So what I'm hoping you're seeing here is that we can take pieces from previous lessons and combine it with this. If we're taking our LOL charts from lesson 1, and then we're going to take our spring energy, and our work from lesson 2, we can take our spring energy from lesson 3. So we're starting to stack these lessons on top of each other to really get an understanding of how can we use energy to a more complicated level. All right, that's all I have for this lesson. Please let me know if you have any questions.